We will look at how the equations of motion get simplified just a little bit for the ocean compared to the compressible fluid in the atmosphere. This was our system we were dealing with, this ellipsoid with longitudinal direction, latitudinal direction, and the local Cartesian coordinate. We projected the rotation locally as f, and we did all our equations of motion, which looked like this, deceptively simple, where we haven't said what rho is like in the real world. It's not a constant, obviously. For the atmosphere, a strong dependence on temperature and pressure, so we always try to get rid of it by using the pressure coordinate and the ideal gas law. In the ocean, on the other hand, we can assume that it's basically a constant reference density, and there are variations around the reference density sigma that we looked at and we will look at again. So the equation looks almost the same, except we have replaced rho by rho ref. So it's du dt plus 1 over rho ref dp dx minus Fv equals Fx, the friction term, dv dt plus 1 over rho ref dp dy plus F times u equals Fy, the frictional term in the meridional direction, right? So let's first handle the hydrostatic equation and jump right to geostrophy. How would geostrophy be simplified in the ocean? It turns out that it's remarkably different from the atmosphere, basically because the geostrophic currents near the surface can be done as independent of density variations, because the sea level variations from the depth are larger than the horizontal density variations. Okay, so what do we mean? So let's look at this system where we are have a height of the free surface. What do we mean by that? This is the deviation from the geoid. What is geoid? We will see in a minute that geoid is basically the sea surface you would get if you turned off all the winds and tides magically and only left gravitational force and rotation. How would the system balance? What does that remind you of? That's our water tank, right? We had rotation and gravity, and there were no tides, there were no winds, and we had created a solid body rotation and the reference parabola we called eta. That was the surface that was perpendicular to the local plumb line, right? Something like this in the ocean is also possible. So eta, sea level, is basically deviation from that reference geoid, which we will see in a minute. So we can look at two depths. Z1 is much deeper than near the surface Z0, and near the surface the density variations will be smaller than the height variations, and that allows us to write the hydrostatic equation into Pz equals Ps, which is up here at the sea level, sea surface, minus G rho ref times Z minus eta. So this difference. Remember, we are going down, so we have to kind of do things this way, right? Because Pz is increasing with depth. In the atmosphere it was exponentially decreasing, but in the ocean it's not exponentially increasing, it's just almost linearly increasing. So in the atmosphere, on the other hand, we start with the hydrostatic equation. We wrote dp dz equals minus g rho ref plus sigma. This is still the ocean actually, not the atmosphere. And we neglected the contribution from sigma because near the surface sigma variations are small compared to the eta and eta variations. Okay, so that's how we got this relation Pz equal Ps minus G rho ref times Z minus eta. What do we do with this? Obviously, we can do dp dx and dp dy, and eta sea level is also a function of x and y, which means near surface geostrophic velocities can be written in terms of the derivatives of the sea level slopes, or derivatives of the sea level, the slopes of sea level in the x and y direction. That's where we are going with that. Revisiting the atmosphere, we had written Pz as Ps times exponential minus z over h, where h was our scale height, remember? And geostrophic currents vectorially were 1 over f rho z hat cross grad p, and our struggle was always to try to get rid of rho using hydrostatic and ideal gas law. So UGVG in this case we're just minus 1 over f rho dp dy and 1 over f rho dp dx before we simplified anything. We looked at large-scale circulation, and we have to come back to Rossby number, right? It's Rossby number that's important for geostrophy, for geostrophic balance at large scale. We need Rossby number to be small, and we looked at the pressure height contours of the 500 millibar surface, and we had shown that most places Rossby number is of order 0.1, 0.2, well, but if you look at an instantaneous chart at 12 GMT on June 21, obviously you end up with these cyclones and anticyclones where Rossby number actually gets close to 1. Okay, here it's almost 0.9. Rossby number is approximately defined as this. It's actually V or FL, where V is the magnitude, typical magnitude of winds, L is the scale over which the winds vary, and F is the local Coriolis. When you do a small enough scale, you can assume it's constant. In the ocean, when we plug in those numbers, we actually will end up getting V of the order of centimeters, L of the order of 100 kilometers, and F, and we'll get, instead of 0.1 in the atmosphere, we'll end up getting 10 to the minus 3. So ocean is also in a low Rossby number regime, which means geostrophic balance should work, which means thermal winds should also work. And there are horizontal gradients of density, as we already saw before in this chapter. We looked at the meridional sections zonally meaned and in the Atlantic, and we showed the subtropical gyres and the upwelling in the tropics, etc. Right? So there is horizontal gradients in density which will give us shear of geostrophic currents in the ocean as well.